So over the next 2 days, we'll see a bunch of variations, but we're just going to get started with this first one. You've got sine of x in 2 locations. So what would you guess you would do first? See how your gut instincts are here. Joey? Get like terms on each side. So what would that involve? Keep going. Good. So bringing your 3 sine x's over to the right and then adding your 1 over to the left. So we'd have a negative 1 equals 2 sine x. And then divide by 2 on both sides. And then it's a little bit different than your typical solving equation because at this point you just have to think about it. You can't divide both sides by sine, correct? That would be foolish because sine's not a number. Sine's a functionality. So if you ever tried to do negative 1/2 divided by sine, your calculator would be confused because you always have to take the sign of something. When you hit sine, it opens a parentheses. So you can't just divide the word sine over because that's dividing a word, not a number. So we have to think the sine of what angle equals negative 1/2? How about the sine of what angle equals positive 1/2? 30 degrees, right? So if you're going in degrees, it would be a 30-degree angle, but that would be if it equaled a positive 1/2. This is equaling a negative 1/2. So, Joey? I don't know if that's a general rule I would want to go by because depending on the functionality, that might be wrong. It actually happens to work out in this case. But you've got to really go around your unit circle. Is there a second quadrant angle where the sine equals a negative? No, because sine's always positive there. There is a third quadrant angle because only tangent is positive, which means sine is negative here. What is the measure of that angle? 210. It's the 30-degree reference angle in the third quadrant. So if this is 180, that would be 210. So x could equal 210 degrees. Is there a fourth quadrant angle? Is sine negative in the fourth quadrant? Yes. And so what is the 30-degree reference angle from the fourth quadrant? Andrew? 330. Good. So these are the 2 answers that fall within the range or the domain from 0 to 360. But some problems will tell you they want all the x answers between a certain interval. This one kind of left it wide open. There are actually an infinite number of answers, right? Because 210, if I added on another 360, would put it at the same spot, and it would have a sign that's negative 1/2. Or if I subtracted 360 from 210. So anytime I add 360 k times, where k is an integer, that's what those symbols mean. K is an element of the set of integers. So k could be 1, 2, 3, 4, 5, or -1, -2, -3, and that will give, this actually gives you all of the solutions. And the same thing with the 330-degree angle. If you add 360k to that, it'll give you the infinite number of potential coterminals to 330. So we just gave our answers, and we gave all of the answers in degrees. Sometimes in the directions they'll specify in radians. So what would this be in radians? my mind first says, well, what's the reference angle in radians? Pi over 6. So if this is 6 pi over 6, this is 7 pi over 6. So if we're doing radians, x equals 7 pi over 6 plus, how do you get a coterminal in radians? What do you add on to it? Two pi, right? For degrees, you add 360 k times. For radians, you add 2 pi k times, where k is an integer. And then in our fourth quadrant, what is the radian measure of the 330 degree angle, Nate? Let's go back to square one. What's the reference angle of it? Reference angle in radians, pi over 6. So this is 6 pi over 6, a half circle. What's a full circle? 12 pi over 6. So what's one tick before 12 pi over 6? 11 pi over 6. And then we want to include any coterminal of that as well. So this particular solving question left the door wide open. It didn't specify degrees or radians. It didn't specify an interval. Like a lot of times if they do specify an interval, they'll just ask you for the solutions between 0 degrees and 360 degrees. It didn't specify that, so we had to be creative and give the infinite answer, because there are an infinite number of possibilities. Okie doke? All right. The next one. The tangent of 3x equals 1. So 1 was a little bit different because sine x was just a plain old x. This is the tangent of 3x equals 1. And this does tell us between 0 and 2 pi. So we're only doing one revolution, and we're doing it in radians, not degrees. So at least it kind of pares down what we have to do here. So there's two ways you can go about this. And I'll do one way maybe on this side and one way on this side. The tangent of what angles equals 1? The tangent of what reference angle equals 1? Marissa? Pi over 4. So this, what's underneath my finger, could be pi over 4. Okay? And it gets complicated because what's under my finger is not just x. It's 3x could equal pi over 4. And that, by the way, that's just the first quadrant version. All students take calculus. What other quadrant could my answer be in, Mitch? The third, and what would that angle be? Right, the tangent of 5 pi over 4 could equal 1. So 3x could equal 5 pi over 4 as well. Okay, so if I solve these two, I would have to solve for x. I'd have to divide both sides by 3, which would give me x equals pi over 12. And if I divided both these sides by 3, I'd get x equals 5 pi over 12. My x's have to be between 0 and 2 pi. Are these answers between 0 and 2 pi? Yes, right? But I still have room for more, right? I'm not even through pi over 2 yet. Everyone see that? So what would be, I just hit the first quadrant, and then I hit the third quadrant, and then I went around again, and when I get to the first quadrant again, what would that angle be? This is 0 pi over 4. This is 4 pi over 4. This is 8 pi over 4. So this would be Connor? 9 pi over 4. So 3x. Now x couldn't be 9 pi over 4, but 3x can be. And then when I solve that, I divide by 3 on both sides, and x equals 9 pi over 12. So essentially, I want to keep doing this until my x answer surpasses 2 pi, at which point I'd have to stop, right? So if I go, so again, 0 pi over 4, 4 pi over 4, 8 pi over 4, 12 pi over 4. So Olivia, this would be, okay, so 3x could equal 13 pi over 4. Divide both sides by 3, and I'd get x equals 13 pi over 12. Do I still have room for more? I do, right? So keep going. So 12 pi over 4. The next would be 16 pi over 4, which would make this what, John? Yep, 17. So 3x could equal 17 pi over 4. Divide both sides by 3. That would give me a solution of 17 pi over 12. I'm getting there. And then keep going. So that was 16 pi over 4. So this would be 20 pi over 4, which would make this what, Morgan? 21 pi over. So 3x could equal 21 pi over 4, which would be x equals 21 pi over 12. Can you pick up on the pattern yet? What do I keep adding onto my x answers? 4 pi over 12, 1 pi over 12, 5 pi over 9, 13, 17, 21. So my next one would be 25 pi over 12, but that surpasses 2 pi. So we're done here. Okay? Now, the other way, and those are our 6 answers. 1, 2, 3, 4, 5, 6 answers. The other way to think about this is if x has to be between 0 and 2 pi, what would 3x have to be between if you multiplied everything by 3, just to kind of make it match that? 3x would have to be between what and what? Bailey? Right. And so that can kind of shed some light on the fact and the reason behind why we went around our circle 3 times. Right? The first time around the circle got us to 2 pi. We had 2 solutions in that rotation. And then the next time around got us to 4 pi. We had 2 more solutions in that rotation. And then the last rotation brought us to 6 pi. Does that make sense? So that can give you some foresight as to how many times you're going to have to go around this circle. And so all of our 3x's stayed within 6 pi. And then we were done. Okie doke. All right. Next one. So let's do this one this way. It's not the sign of x, it's the sign of x divided by 2. So if x has to be between 0 and 2 pi, then x divided by 2 has to be between what and what, Mackenzie? 0 and pi. So when we go around and we're looking for all the places where sine equals root 3 over 2, we're only looking from here to there. So what could x over 2 equal? What is the, and again we're in radians. So Bridget, what, the sine of what kind of angle equals root 3 over 2? Pi over 3. So x over 2 could equal pi over 3, which multiply both sides by 2, and x equals 2 pi over 3. And x over 2 could equal, what's the second quadrant angle? Since sine is also positive there, we're going to include that. What would that be, Aiden? Right, because here's 3 pi over 3. So one tick before that would be 2 pi over 3. And then if you actually solve for x by multiplying by 2 on both sides, x equals 4 pi over 3. And there are your two solutions. See, having x over 2 between 0 and 2 pi, or I'm sorry, having x over 2 between 0 and pi ensures that when you double it to solve for x, x stays between 0 and 2 pi. Capiche? Any questions on that? So knowing your memorized values, obviously that's important again. Understanding the quadrants in which sine is positive, tangent is positive, sine had to be negative, so the understanding your quadrant stuff as well. And then kind of knowing how a change in period or a horizontal stretch or compression affects your domain. What do you make of 4? What's the first thought that comes to your mind when you look at 4? I see a trig function, but I also see a different type of function structure. Joey, what's your gut? Okay, he was thinking a double angle, but that would be if I had, wait a minute. That wasn't so much, which double angle are you thinking? So he's seeing 2 cosine squared theta minus 1. So he's seeing this, and he's thinking maybe I would replace that with the cosine of 2x plus the cosine of x equals 0. The only challenge here now, though, is now you have kind of a mixture. You're not taking the cosine of the same angle both times. Does that make sense? It's a little. If it was the cosine of 2x plus another cosine of 2x, then we could combine like terms. But this actually probably creates a bigger problem. So I like your thought. I have to be honest with you, I don't use the reference sheet very much for solving. I'm not going to say I never do it. If I actually got into a pickle, I would. But I want you, when you look at something like this, to start seeing a quadratic. You've got a squared term, a regular term, and a constant. That's a quadratic as well. So we're going to solve this sort of by factoring. So when you guess and check, you have 2 cosine x and a cosine x. The only way to make a 1 is with a 1 and a 1. And then you just have to play around with plus or minus. If you want your middle term to be a positive, then you want the 2 cosine x product to be the positive and this one to be the negative. And then just like any other quadratic, you tee it up. So 2 cosine x minus 1 equals 0, or cosine x plus 1 equals 0. And if you're solving the first one, you have that cosine x needs to equal positive a half. So let's look at that one. Since x has to be between 0 and 2 pi, we're going to look for all the places that cosine equals a half between 0 and 2 pi. So one rotation. Is there anything in the first quadrant? Olivia? Any x value in the first quadrant where the cosine equals positive a half? Pi over 3. So x would equal pi over 3. Anything in the second quadrant, Abby? Nope. Cosine is positive, so there's nothing there. Where's the next quadrant? We're going to have something. The fourth, and so what would that be? 5 pi over 3. So there's two of our solutions from teeing up that side. And then on the next one, we're looking for where the cosine of x would equal -1. So where would that happen, Andrew? Just pi, right? Because the cosine of 0 is 1, and then it decreases down to 0, and it continues decreasing down to -1. So that would just be at pi. And you have 3 solutions to that. So if there's a quadratic to be factored, go ahead and do that. That's the takeaway from that one. What do you see on 5? Sarah? What do you mean? The Pythagorean identity? Sine squared x plus cosine squared x equals 1. But this isn't a sine squared x minus 1. It's 4 sine squared. You can't break that. If this was in parentheses, fine, because then it would be 4 times the whole thing. With the 4 just on the sign, it's not intended to be multiplied by the whole thing. Not only that, but just be careful. Sine squared x minus 1 would actually equal a negative cosine squared too, if anything. But because that 4 is there, you can't do that. Olivia? Yeah, just factor it. I would stay away from your reference sheet and substitutions unless you're absolutely in a pickle. But again here, just like the previous one, this is factorable. This is the difference of 2 perfect squares. So you have 2 sine x plus 1 and 2 sine x minus 1. And then we tee it up and solve. So on the first one, the sine of x would equal -1/2. And on the second one, the sine of x would equal +1/2. So this one's interesting because it's the same number every time. It's a half both times. But it's including both positives and negatives. So we're actually going to hit up all 4 quadrants, right? What would the reference angle be, John? Nope. Pi over 6. So the first quadrant version, which will give you a +1/2, is pi over 6. The second quadrant version, which will also give you a positive, is what, Marissa? 5 pi over 6. Very good. The third quadrant version, which will give you a -1/2, is what, Trista? Yep. And the fourth quadrant version is what, Nate? Good. Any questions there? Okay, and the last one, number 6, we, for the first time, sort of have a mixture. We have tangents and we have sines, which hasn't happened before because all of the previous ones were all tangents, all sines, or all cosines. So in something like this, you're still going to want to factor. You want to get it equal to 0. You want to factor out a tangent. And you want to tee it up. So when does the tangent of x equal 0? And when does the sine squared of x minus 3 equal 0? So starting with when does the tangent of x equal 0? Olivia? Pi is one answer. You missed one though. So, and 0, good. And on this one, we're going to have to add 3 to both sides. Square root both sides. So the sine of x has to equal plus or minus root 3. Mitch, what are your thoughts there? Root 3 is not one of the values, right? So you've got, what, 0, 1/2, root 2 over 2, root 3 over 2, and 1. So then what? What else do you know about root 3? It's not one of your values. And what's the, Andrew? It is one of tangent's values, but we're not dealing with tangent, so that's a dead end. What is the approximate value of root 3? What's the square root of 3? Is it 1? Is it bigger than 1 or less than 1? Is it 2? Is it bigger than 1 or less than 1? Or bigger than 2 or less than 2? Less than 2. So the answer, this is somewhere between 1 and 2. Guess what? The sine of an angle is never greater than 1. Right? The sine of any angle has to be between -1 and 1. Think about your sine graph. It fluctuates between 1 and -1. That's out of the appropriate range. So there are no x values that will make that true. Good? Okay, so getting your sines or cosines all by, or tangents or whatever it might be all by itself, understanding how to deal with a change in domain, if there's a horizontal stretch or compression, and understanding how to factor and tee it up and still solve that way. Good? All right, so your homework, page 619, 1 through 61, 1, 5s, and 9s.